Like there will be a lag of 20 to 25 seconds, sir. But we are live only, sir. I'm just checking whether audio is fine.
But I need to have a...
No, sir. It's inbuilt mic, sir.
It's there.
So, yes, sir.
Yeah, I'm here.
Yes, sir. You are live only, sir. So you can introduce and start the session, sir.
So there are only two. Four are...
Yes, sir. Audio is working fine, sir. Yes.
Okay, hello everyone. You're seeing me again. Welcome to this live session of this online NPTEL course, Structural Geology. So I'm here to answer your questions, and with me I have two of the teaching assistants who worked extremely hard in this semester to make this course successful or effectful, let's put it this way. So yes, Saqib is with me. Saqib. So yeah, here you see Saqib. And Manav, would you please come? So here is Manav. So please type your question on the panel and I'll help you to answer.
One question, please.
Oh, okay. So rock failure is essentially something which we deal mostly with the fracturing of the rocks. So where it is mostly considered under brittle deformation. Folds and others, these are also a kind of failure, but these are plastic failure. rock failures, therefore, you can classify in two different ways. In one case, where you produce permanent deformation, either by forming a brittle deformation or by plastic or ductile deformation. So folding or ductile shear zones, this kind of features are generally considered under ductile domain, and fracturing, boudinage, faulting, this kind of things are considered under brittle domain. The first one, where you consider folding or ductile shear zones or any ductile deformation, these are essentially being governed by laws like von Mises failure criteria, Tresca's criteria, and so on, where you involve the second stress invariant, particularly in von Mises failure criteria. So that considers the yield and then progressive deformation without producing any fracture. Whereas in the brittle deformation, you have a series of failure criteria, and most commonly used criteria is von Mises failure criteria, and there are many others. So I have covered this in the lecture. I think I gave you an answer. Is this clear to you? Okay. Projection of fold and fault on the stereo net, Sudeep. We actually do not project the fault or fault if you think of their geometry. What we actually do, we project or we represent the elements which are associated with the folds and faults. For example, if we are considering fold, we cannot project the entire geometry of the fold, but we select some of the structural elements, could be planar, could be linear, and by looking at it, we can figure out that what is the geometry of the fold. And very similarly, we can do it with the fold. I just give you an example here. Say if I look at, then say you're considering a stereo net. Mostly projections in structural geology we do with stereo net. So you can consider this is your stereo net. Just consider it this way. This is your north, east, south, and west. And say we're talking about a fold which is something like that. There were a series of assignments on this. And if we have to plot the strike of these beds, then we can see clearly that you see the strike of the beds are constant, right? But the deep angle would vary. So therefore, if we have to plot it, say this direction or the direction of the fold axis, the trend of the fold axis, for example, say 45 degrees. So the strike could always be here. So that's the strike of the 45-degree trend line, or this is the trend line of the 45 degrees. And then we see the strike is constant, but magnitude of the dip and their dip directions are varying. So if I consider this limb, and this side would be essentially your southeast direction. So here the inclination is extremely less. So the strike would be something like that, and then so on it is here. So this is very low, so this would be here, and slowly when I approach towards the hinge of this fold, the dip angle would increase, and therefore we go this way. And now if you consider the other limb, which you don't see, but this side limb, all the beds are dipping on the northwest side. So therefore, from the hinge towards the limb, the strikes would remain same, but the dips would vary. Right, so again from the limb to the hinge. And therefore you see that there is a reversal of the dip, and these, or this one, is essentially your fold axis. And you may consider this as your axial plane. Now imagine the fold is something like this. What do we see here in this kind of folds? Of course, this would be your axial plane in that case, which is vertical in this form. But the strike from here, you can clearly see that strike is changing, but dip is more or less constant. So in that case, if I have to define the fold in a projected form or in the stereo net, then in a very similar way, I see the strike is changing, but dip is more or less constant. In that case, and in this case, dip angle is almost vertical, so 90 degrees. So therefore, all your projection lines of the strike of the beds would simply go like this. So they are all vertical, but with different strike lines. Something like that. And therefore, the fold axis would come here. And you can clearly see that fold axis here is vertical. In this case, it was horizontal, so fold axis falls on the periphery of the stereo net. So in general, to answer your question in summary, you don't consider this you don't project the entire fold this way, but you project the elements that you can measure from the fold, and then you represent it in the stereo net. I hope I answered your question. Oyun, that was Shudipto. Okay, Anderson theory of faulting, Oyun. Yes, I did not teach it properly. Anderson theory of faulting. I did not touch it in my lectures, to be very honest. But in one of the tutorials, Sakib mentioned it in detail, what is Anderson's theory of faulting. And right now, I'm really not going to explain it. You just type it in any search engine, you'll figure it out. Or I request you to look at the tutorial video or lab video that we are talking about. Sakib, one of the TAs, he has explained what is Anderson's theory of faulting. You just have a look there, Ayun, and I'm sure you can figure it out. Or could you please tell me which tutorial it was?
Paleo stress analysis.
Yes, this was related to the paleo stress analysis, and there you can get the Anderson's theory of faulting.
That link also, no sir, if you want, you can copy paste that link.
Yeah, but I think they have everything,
Right,
so
no
they can
links.
get it. So Ayon, if you are confused, you please write me later. I can send you a note on Anderson's theory of faulting. But I looked at this lecture and Saqib presented it very well. So just have a look. Sit on. Yes, please, Ram Kiran. If I can, I certainly answer your question. Just type it here. Good evening, Gurvinder. Well, Gurvinder, your question is, does kinematic and dynamic analysis of deformation include actually stress and strain only, or also the mechanics? Uh, yeah, I mean, stress and strain, these two are essentially an integrated part of mechanics. So yes, this includes. So kinematic is essentially you deal with strain, and dynamics you deal with stress and other mechanics. So it's just not stress and strain, but many other things, and that's why mechanics is the broader term, the umbrella, and then strain and stress, these are two pillars of the subject mechanics. Murli, there is an issue with the thing I see.
Sir, just refresh the file. Let me just see whether the internet is working fine only, sir.
So I just start this.
Yes, sir. Yeah. Thanks.
Murli,
Yes.
can you please ask for a couple of
Yes.
start this?
Okay.
Raj Kiran, you wanted to ask something, so please go ahead. So two questions are there. I first take Oyon's question. Did we discuss how to determine the throw in a contour map? Okay, so this part we did not discuss, but we take a note, Oyon. So both of your questions we are not answering because this is somehow out of the syllabus. But you certainly can send me an email. I will answer you this question, Oyon. So, and to be very specific, that your question that throw you can measure if you have some other parameters known, but generally you get it from the lithomap. But we'll come back to you on this. You just drop me an email. And now I'm taking the question of Raj Kiran. Sir, I have seen your CV and you have done most of your work in rheological domain, which includes working with the processes of IPT. So obviously you must have done works in the lab, and in university it is hard to find these labs. Yes, in India we don't have this kind of facilities. That's very much true. We have few facilities, but I first answer your question in a philosophical way, that not necessarily you have to have all the instruments to answer the research questions. There are terminologies like analog experiments. So you can think of this, and India in particular is extremely rich in doing this kind of research. We have a good amount of laboratories in different institutes, not only in IITs, but also many universities and colleges. They have very good laboratories where they do analog experiments, which are easier, less expensive, and also easy to observe and demonstrate. Coming back to your question, that yes, you can do it. So in IIT-Kanpur, I'm building this kind of lab. There is also another lab which is in action, that is in Jadavpur University with Professor Nibir Mandal, but he does work in a different scale. And if you would like to include deformation part, then yes, these two are the only possibilities. But if you'd like to observe the high pressure temperature behavior without much attention on the deformation part, then there is one laboratory very well-known laboratory that's in Allahabad. And in IIT-Kanpur, they recently developed a laboratory on high pressure temperature observations. So this is a kind of piston cylinder. So you can also have a look there. And yes, what is most important in working in any direction, you have to have a good theoretical background. Learning experiments are difficult, very difficult to run it, to process it, to work on this. This requires some special skills. But if your theory is strong, then you can actually invent or innovate new techniques, new designs, and so on. And then once you are ready, you can apply in different parts of the world to continue your work. I believe you are a master student, so for PhDs and other places, you certainly can apply in different places. And if you are good enough, they will take you, no problem. Gurvinder. So yes, landslides. Well, again, I did not include this, but landslides are something that which is a parameter of many factors. And one of the major factors is essentially the structural attributes, the way the layerings or foldings or the weaker planes are there. And then the second part constitutes that when and how these failure surfaces would focus on, would trigger to produce a large or small or a continuous landslide. Uh, I did not work much on landslides with my, so I cannot suggest you right now the works, but yes, I have one paper in the Journal of Landslides, so you can have a look to that work. So there we try to focus on how the orientation of the layers trigger landslides, or the extent of the landslides, how it could be a function of the orientation of the layers of the slope. And most of the landslides, as you know, are triggered either by earthquakes or by rainfall and so on, and there are database for that. There is one blog of American Geophysical Union. You just search landslide blog, AGU, in your search engine. You'll find it, and you get all sorts of data related to landslides, the sort of inventory of all the landslides you can find in that blog. Um, Yes, so Dave Petley runs it. So I'm typing you the web link of this blog, so you can have a look and figure it out. T. Microscopic folds. What do you mean by microscopic folds, Gurvinder? And I mean, what would you like to know about it? So, how to relate thin section studies to large structures? This is something that you have to be very careful that what you'd like to interpret and what you'd not. Actually, this is something that requires one-to-one or teaching something in sitting with the microscopes. But certainly you can refer the book of Professor Pashkier and Trau, this microtectonics. There are also many other books where you can figure out that how you have this data from the thin sections or observation from the thin sections, and then you can relate it to the large scale structures. I would like to also mention one thing here, that the general ideas of studying microscopes is not always to relate it to the larger picture, but to understand the processes. So once you understand the process, then you can think that this process should be there more or less in the region, because there are some typical cases, but if you study a thin section of some quartz grains and you see that these quartz grains are showing some sort of evidences of dynamic recrystallization, then it did not happen just the place where you have collected the sample to study the thin section. It must have happened regionally. So that tells you that, okay, the pressure and temperature of that region should be that where quartz could deform through the process of dynamic recrystallization. So this is how you interpret. So therefore, the region has experienced or had experienced a pressure and temperature of such and such. And from these you can explain, okay, so if that place has experienced this much of pressure and temperature, then maybe in 10 or 15 kilometers you see a different assemblage. So that tells you that, okay, the temperature gradient could be like this, or pressure gradient could be like this. So this is how you employ your microstructural study to a large scale. But I can right now just tell you this, but I have a plan of offering a course on microstructures in future. Let's see if I can manage it, but we'll figure it out. I hope I answered your questions. Okay, to continue, basically thin section studies that we do in structural geology. Yes, you must have a look of this book, Pashkier and Trau. The name of the book is Microtectonics. There is one more book of Professor Blenkinshaw, and the pioneer of all these kind of books is Professor Vernon's book. And if you'd like to relate structural geology and metamorphism, that I always would like to prefer and love to do, then there is a book of Fry, Metamorphic Textures. So this is also an excellent book that you should read. But having said that, understanding only microstructures is not going to help you much. You have to always make your theory very strong. Oyon has asked another question, how repetition indicates structural sequences like syncline, anticline, fault, homocline, etc. So you cannot so there are techniques. Again, I did not teach this, but I tell you, for syncline and anticline, you cannot identify whether this is synform or antiform just by looking at the reputations. You have to have the data of the strike of these beds, and that only can tell you that whether you are on the synform or antiform. And then looking at the stratigraphy, that whether you are going younger to the core or going older to the core, that then defines you whether you are in syncline or anticline, or it is antiformal syncline or synformal anticline. Similarly with faults, you have, I request you to read the book of Professor Ghosh on the fault chapters. And there you can figure out that in faults, we have always, there you always have repetition of strata or omission of strata. That both can happen with the faults. Again, I did not cover this because of time. But what happens, again, you have to figure out in different processes that you can draw diagrams by yourself, and then you can also tilt the beds in different way with respect to the fault planes and figure it out, how does it work. Is this answer clear, Ayon? Just to confirm, then we can take the next question. So there are many who are online, but not asking questions. I can see that. If you have questions, please write. Otherwise, there is no point of wasting your time and my time. So you can conclude this session, and I then have to wish you best of luck for your examination. But just if you have questions, please ask. Do not hesitate. If I can, I will answer. If I can't, I won't. Simple. Thanks, Ayon. Gurvinder, again, so there are many applied aspects of structural geology. I taught you in this course, particularly at the very beginning. I explained what are the uses of structural geology, and during the course, before each and every subject, every topic, I explained that why we need to study this. And for engineering geology in particular, yes, failure mechanics, understanding the behavior of the rocks, their composition, foliations, etc., etc. So these are all very, very important in structural geology. But again, this is not a course of engineering geology. So this is an undergraduate level course where the main aim was to introduce mostly the different names, their meanings, and partly the processes. But if you study engineering geology now or engineering structural geology, then you can actually relate these terminologies with this. But in brief, yes, the applications are very, very significant. You can consider the orientation of stress would be different in an open tunnel. When you're trying to build a dam, or if you have a very deep tunnel or open tunnel, it depends on the rock mass, it depends on the regional stress factors, and at the same time, what is the overall structure of this region, if it is within the fold or if it is within something. It also helps you in drilling the or making the holes in the rocks. I just give you a very simple example. Say, let's clean this. Or I just add a layer. Say, for example, Gurvinder, you have a folded layer like this. Okay. And then you have the surface. So this is the cross section you're looking at, 3 different layers, and this is going like this. And if you're trying to dig a hole here, and let me extend it to the 3rd dimension, so you can clearly see that the layers are going like this. So if you try to dig the tunnel here, so if you try to dig the tunnel here like this, you know more or less what is going to happen throughout the path of the tunnel. But if in that case the fold is upright and horizontal, but if the fold is plunging, something like that, then you clearly would encounter different layers at different lengths of your tunnel, and that you need to know. For example, you don't know that there is a fault. Say this can be, there could be a fault like this. Very simple example, you just can think by yourself. Okay. And when you're trying to dig a tunnel from here and you are going inside, you're very smooth here, but when you approach here, you'll see a fault, and you can seal it, or you can take necessary things out of this. But again, you have to take care of this fault. So unless you know that there is a fault, so you can have your measurements or estimates accordingly. So therefore, you need a structural geologist who would survey this region and tell you in advance, hey, there is a fault. So you make your cost estimates or instrumentation accordingly, and so on. So this is how it works. These are very simple examples, but I'm sure you can have some other ideas out of it. Thank you. You're welcome, Govinder. Pushkar. Your question is, how can I use soft sediment deformation and other sedimentological info in tandem with structural data to study new tectonics? This is in relation with Himalayan rivers. Yes, soft sediment deformation are very, very important, and these actually do influence a lot in terms of, not influence, but they provide a significant information regarding the deformation, the flow structures, and so on. Structural data to study neotectonics, this question is not very clear to me. This is in relation with Himalayan rivers. Could you please elaborate your question, Pushkar? Then that would be helpful for me. I'm not very sure that that I have understand your question. Yes, Gurvinder. I can't remember what is the chapter, but you can certainly refer the book of Professor Ghosh, and also books of Ramsay, if it is available in your library. There is a folding and fracturing of rocks. So that's very, very important to read. But I think I covered the entire superposition folding in detail. But yes, Professor Ghosh's book is good for that. Certainly can look at it. Or if you have the book of Professor Tuis and Moore. So these books are excellent study materials for understanding not only superposed folding but the entire structure. Oh, Pushkar, now it's clear how to relate the soft sedimentary deformation with the thrust system and their current movement. Again, this is something that you have to see. This is not really something of undergraduate level. But yes, you have to see the vergence and other things of the fold thrust belt. And yes, in the reverse sections you may see different kind of thin sedimentary structures, and that can be further modified with different things. So you have to what I would do if I were in your class, without much confidence of that subject, I probably would take a lot of data, as much as I can, different structural data and so on, and then I'll try to plot it and see how, whether these are giving me some senses or not. So that's a very brief answer I can give you. That may not give you very, very detailed insight. But to read something, I don't remember anything right now, but there are many work related to fold thrust belts, where you can actually see different kind of structures, whether when you're approaching from the hinterland to the foldland of a thrust belt. So just you can see these kind of features, the debris flow and other things. These are also included in this part. So yes, I'm not very happy that I could not give you the proper answer. But maybe you can send me some images or some other features or sketches that we have from the field, so we can discuss more on that. Any more questions, friends? Sudeep, again, I did not teach this Moore circle for plane stress and strain condition. Uh, it was not really the topic for undergraduate studies, but if you want, you can read. Just type online. You can get a lot of materials. Uh, the point is, in this course, there are many students who just started their career or their student's career as a structural geologist. So it's important also from my side that I do not load them with too much information, and they will be scared. So I understand you are an advanced student, so you're studying it, but it has to be very general. I gave a very detailed, not very detailed, but very initial discussion. What is Moore circle? How you plot it? How you use it? Uh, but I really am not going into that part, what is Moore circle. But again, I have a plan of giving a course on advanced structural geology, and there we may take all these kind of features of different kinds of Moore circle and so others. Gurvinder, if you write strain hardening and softening, that's not a question. I don't understand what it is. So please elaborate your question. Yes, Gurvinder, both strain hardening and strain softening, these two are essentially under the ductile domain. If you remember, I showed all of you a plot, something like that. Let me come back to you. This. Sorry. Yeah. So if you remember, we have plotted something. So here in this axis you have strain, and here in this axis you have stress. And we have shown that materials can deform in this section very different ways. So one, you have yield stress here, and then it can fail, and then it can go further, and then it can continue. So this part is hardening. Or it can flow at a constant stress. Here you need more stress to deform the material. So this is steady state. And you have something like that. This is softening. So whatever is happening in this domain here, this is brittle. And these things are essentially happening in ductile domain in general. But when you see these things after performing an experiment, we figure out that these are not necessarily typically ductile. It actually involves sometimes with some composite materials. That means you're not dealing with a single phase, but when you deal with the multiple phases, one very strong, one very soft, then we see that there is some sort of brittle ductile deformation do happen, but the rocks do not produce a large scale or not large scale, but sample scale structures. So these are something that you need to consider. But to answer your question generally, yes, these are essentially in the ductile domain of deformation. Where, Oyun, you have another question? Yes? Yes, Oyun has a question where will be the pole of pi s circle in the stereographic projection? So who will answer this question? Where will be the pi s circle in the stereographic projection? What is the meaning of this pi s circle?
I also don't know. Pi s circle means pi s
One is
circle.
pi and other is beta.
So what is pi s circle?
Maybe new terminology, I don't know. So Oyun, please explain what do you mean by the pi s circle? You see from a thrust fault. That's a question from Shudeep. What is UC?
Differentiated. Uncool.
Yes, Gurvinder, I'll try. I'll try my best. Thank you. Okay. Look, if unconformity and thrust fault, yes, that's an interesting question. I remember in my classes I used to have those, but let me try to explain you. So if it is a thrust fault, then and if you have to confuse it with unconformity, then you must be talking about angular unconformity, right? So in angular unconformity, if this is your unconformity surface, then you have your things below the plane, something like this, and above this you would have horizontal planes like this. Okay, so that's your unconformity plane. I use your language, you see. Okay, you see. Now, so this is angular unconformity. But if you have a thrust fault, say a very low angle thrust fault, then again you have this kind of features. But at the top of this unconformity, if you have to consider this as an unconformity, then I cannot have layers of a horizontal manner. I must have something in a very similar way which is going on. So if this one is this layer, then this one has to be this layer. And this clearly tells you that this is not an unconformity, but a thrust contact or nappe contact. But of course, this can erode out, and then beds can deposit. In that case, honestly, I don't know whether you will call it a thrust contact or an unconformity. But looking at the definition of angular unconformity, I would certainly call it as unconformity, not a thrust, because the thrust geometry has gone. I hope I answered your question.
We can answer Shudip's question if we omit the S. We don't know what is a
No,
pi.
Shudip, Oyon.
Oyon's question, if we omit the S, we don't know what is a pi S circle.
Yes.
Okay,
Oh.
now.
Pole of the great circle.
So that will
The-
represent the fold axis basically.
Pole of
The pi circle represents the fold axis
yes,
of a
yes,
symmetrical
yes.
fold. Now it's clear.
Yeah. So that S term confused because you know I'm a little old. I have white beard, so I don't actually not very familiar with the new terminologies. So yeah, Manav can explain you this. So in this whiteboard, Manav can explain you what is pi and what is what.
So if we consider this as a stereographic plot, so what we do in a pi diagram is that we plot the poles of the folded bedding surfaces. So suppose these are the poles of the folded bedding surfaces. Now if our fold is a cylindrical fold, the poles of the folded bedding surface will fall in a great circle. So we orient the stereo net and the overlay as we have discussed in the tutorial sessions and fit a great circle from these poles. These poles are termed as pi poles. And the great circle that fits through the pi poles is called a pi circle. So this is our pi circle. Now clearly if the pi poles are the poles of my folded bedding surface and then I represent a great circle passing through all the pi poles, then our pi circle is basically the cylindrical or the form surface of the poles. So clearly your question is, if we draw the pole of this pi circle, so the pole of this pi circle will give us the orientation of the fold axis. So the basic use of this diagram is, if we construct a pi circle, the pole to the pi circle will give us the fold axis. Hope now you are clear with your question and that answers your question.
Thank you, Manav. Ayan, I believe this is clear. Oh, I could not see this. Why? Yes. But anyway. Gurvinder, one more question from your side. As we go away from a thrust, the fracture density increases. Is this always true? Yes, if the fractures we are talking about are related to thrusts or any kind of faults, yes, this is true. So in a typical fault zone, you have 3 segments. So the fault zone is sandwiched, fault zone is, or fault gouge, we call it principal sleep zone, where the actual sleep did happen. Then surrounding these we have what we call damage zone, where the concentration of fractures are very high. And then away from this we have relatively undeformed joints, and this is more or less true if the fractures again are related to the faults or thrusts. But it may have some other fractures that we are not going to consider right now. Okay, and then your question is, does joints always form through fracture mode 1? Yes, the way we define joints, these are always mode 1, at least in terms of their genesis. What I mean by this, when the joints do form, they always form in mode 1 manner. But later, these fractures could be modified in mode 2 or mode 3 or even accentuated mode 1 and so on. So then we don't actually consider this as a mechanism of joint formation because joint has already formed. But what we would like to emphasize here, the joints are essentially mode 1 fracture. We have terminology like shear joints and so on, but these are much later processes of the joint formation. Compressional joints, yes, stylolites are sometimes, we call it compressional joints if you have series of stylolites. But that's again something very new terminology. But joints, the way we understand the fractures in the rocks without any displacement or very less displacement along the walls, these are essentially mode 1 fractures. Rajvardhan Rathod. Hey, how are you? Sir, in assignment 11, question number 2, correct option is, okay, if it is related to assignments, then I give it to Manav or Sakib, so they can answer. Rajvardhan, we are taking your question later, but Oyun has asked a question. Can you refer any book for solving numerical problems in structural geology? I remember, Oyun, there is a book, Computers and Structural Geology. Probably it's a journal as well. I don't remember exactly. But certainly you can refer many books that dealt or deal with the numerical problems of structural geology, and certainly you can think of the books of Professor Ramsey, the 3 volumes he has. A lot of mathematical examples and numerical examples are folding and fracturing of rocks, the first 2 volumes, and then strain analysis, the 2nd volume, and 3rd volume is finite element models. So you can certainly look at these 3. It is a large, pretty flat books. Yeah. So I can suggest you the references, Ayan. I don't remember these things by heart, but certainly Professor Ramsey's books are very important in this aspect. You just write me an email. I'll answer your question. I'll send you some materials actually. Professor Taras Garia wrote another book on numerical models, so I certainly can give you some good materials. And Rajvardhan, for your question on related to assignments, so Manav and Sakib, they're trying to look at.
No, the question's answer is correct. Each of the we can provide
So,
you
yeah.
the reason.
So
the
for
question.
reason, you just do you have to explain it with the drawing?
No.
Okay.
Is for a blast what you told you did.
So we are having trouble in the lecture. He has a question with the lecture as well. So we answer the assignment part. In assignment 11, the question number 2 reads as which of the fabric does not indicate the sense of shear, and the answers are SC, sigma type, phi type, and delta type. So clearly, out of the 4 options given, the clearly out of the pardon.
You guys are asking anything to me?
No.
Clearly out of the 4 options given, only the phi type has a symmetrical tail. So when we have a symmetrical tail of an porphyroclast, it does not give the sense of shear, because when you have an asymmetrical tail, the asymmetricity gives you the sense of shear. So in phi type porphyroclast, as the tail is not asymmetric, we cannot determine the sense of shear from the phi type porphyroclast. Right. So the correct answer of question 2 will be phi type. And regarding your second part of the question, what is mentioned in lecture 32 slide 22, we are trying to look at it and then we will answer.
What is there? Okay, let me have a look there. So what is the question? No, what is the question? Let me see. Lecture 32, slide 22, you have clearly stated that porphyroclasts are clearly a very good shear sense indicator. Yes, they are, but with asymmetric geometry. So if you have delta type or phi type porphyroclasts, then yes, they are excellent shear strength indicators, but not the phi type. So porphyroclasts with delta or sigma type mantle structures are good shear strength indicators. Is this clear, Rajvardhan? Just let us know.
See a good shear strength.
SC, yes, it's a very good shear strength indicator. I mean, if you look at the shear zone lecture, you'll see I explain why SC fabric is excellent shear strength indicator. You are welcome, Gurvinder. Okay, so if you don't have any more questions, we will wait a few more minutes, and then we'll stop this live session. Just write if you have questions. Okay, I think we sign off
Yes.
right now.
Yes.
So
in the streams.
oh, Rajvardhan, if I have said it, then I certainly didn't say it right. These three are not essentially good shear strength indicators, particularly phi structures are not. I'll have a look of the lecture and I'll try to correct it. But if I have said this, then I said it wrong. Phi structure or phi porphyroclasts are not at all good shear strength indicators. I'm sorry if I said something wrong. But anyway, I sign it off. Is myelinization in my why feldspar grains or shows okay, so English has an issue, more resistance than quartz. Oh, that's because feldspars are strong than quartz, so that's their rheological property. So quartz do undergo ductile deformation or dynamic recrystallization much quickly than feldspar. So feldspars are strong. That's a property of this mineral. That's why these are. So Rajvardhan, again, I was unable to figure out very correctly. This is in reference to what question? Myelinization, the squads and these things. Mistake, but. Yes. Phi structures are not good shear strength indicators, so we don't take them in account. Only delta and sigma structures. Okay, thank you, Rajvardhan. I think I made your answer clear. So with this, I sign off. Thank you, everyone. I hope you're ready for the exam, which is coming up in the next
November 16th and 17th.
November 16th and 17th. We have the exam. So I wish you all the best. and we'll see, and then I'll be sure you keep in touch with me if for any question. This live session is just a formality, but my email is always active, so you can send me any question anytime. I'll be more than happy to answer and help you.
You can write in the forum also, sir. Whatever questions.
Yeah, you can also write in the forum if you'd like to, and I'll be more than happy to answer there as well, together with my teaching assistants Manav and Sakil. So thank you everyone. I'm signing off. Wish you a very nice evening. Thank you.